So let's go to calling conventions. Calling conventions, guys, is very important because when you are doing analysis, you wanna understand the functions and the parameters that are being used by those functions. And that's very, very important, guys, because basically you will see a function that receives three parameters or whatever number of parameters, and you want to trace those parameters, how they are being used, so that you can understand the flow and get to the meat. And then that's why the calling convention comes into play, because the calling convention is going to tell you how the functions are reading those parameters. What is the format of those parameters? Are they being sent to the function through the stack? Are those guys are being sent through the registers? How these parameters are being sent to the functions so that I can follow them inside whatever function I'm tracing. Okay, that's very important. So if you are doing this analysis on Linux, it's a different calling convention than Windows, and it's a different convention if it's 32 bits or 64 bits. Okay, let's see how this works. Before of that, you need to understand the stack. The stack, guys, is a place, temporary place in memory that is being used when you call a function. It basically stores the parameters and the variables that are being used by the function for it to be calculated, and then you finish the function and the stack disappears. You call another function, another temporary stack is being created, and that's the way the stack is being used for these temporary cases. Let's see how that works. Okay, so it's called LIFO, last in, first out. What that means, guys. Okay, so again, don't worry, you're gonna see this many times. You're gonna see in the lab and you're gonna understand. But basically, in 32 bits, when you call a function, the values are gonna push into this stack, imagine in memory. Let's see how that would look like. So let's say that you said, hey, I'm gonna push a number 1 value into the stack. It goes to number 1. And then you say, hey, I'm gonna push also another value, which is another parameter. Let's see that. Let's imagine that the function is gonna have many parameters, and I'm gonna push the first value to the function, which is number 1. Then I'm gonna push a number 2, and let's see, in the left side, imagine that this is the address in memory. Okay, this is very important, and the right side is the value. Okay, see this, 204 is the memory address. When you push the next value, is 200. In the address 200, you push the second value. Then the third value, the third parameter, you push the third value. What you are noticing here, guys, in the addresses, they are going downwards. You see, this means that the address in the stack are being pushed downwards. Basically means that if the address in the stack is in 204, the next values are gonna be in the lower addresses of the stack. Don't worry about this, guys. It's not easy to understand at the beginning, but you will catch it with many exercises. Okay, so in this case, we're pushing number 1. Imagine that the function, we send the number 1 value, then we send the number 2 value, 3, 4, and 5. Okay, at this point, we send five parameters to the function with the values 1, 2, 3, 4, 5. Okay, then if we wanna get out one of those values from the stack, is called a pop instruction. Okay, so what the pop just did, guys, you remember the last in, first out? Which was the last that get in? The number 5. You remember? This was the last to get in. When I do the pop, the first thing that is gonna be out is this guy. Okay, out of the stack. Pop, you see, this one F4 number 5, it gets out, and then now the stack is only holding these remaining 4 values. Okay, that's basically a quick way to understand how the stack works. Let's do it again. Okay, the stack is like pushing value, value, value. The addresses go downwards. Okay, then if I do a pop, get the first value out. If I keep doing pop, I will get then the 4 out, then the 3 out, all the way to the 1. Okay, I just did 1 here, but that's, you get the idea. Okay, so let's see this a little bit more in detail of the stack. So this is how the stack looks like. The ESP is a register in 32 bits that points to the top of the stack, which means where are those values being located. What I just explained you guys, like this guy here, the last guy added, this last guy added one located at 1F8, exactly here is where ESP is pointing to, at the top, which is exactly this guy at the top. Okay, so this is ESP. Then you have EBP. EBP is basically the base of the stack, meaning where the stack started growing. Okay, let's go back here. The base would be exactly this guy. This would be EBP, the base, where the stack was created for this function. Then start growing, 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 until you get to this last guy, and ESP was here at the top, then ESP was here at the top, then here, and finally ESP points to this guy. When we do the pop, now ESP points to this guy, which now is at the number 4 address 1F8. Okay, guys? So that's the way EBP is always, ESP is moving based on the push and pops, and EBP is always staying at the base. Okay, this is exactly ESP and EBP. Okay, and EBP help us to reach whatever values are in the ESP, and also help us to reach return address. You will see what is a return address in a second. You can see other values that can be passed to the stack. Normally, the values that you see here above EBP are local variables, and the values that you see here, EBP plus 8, C10, 14, those are the arguments that are being, or parameters that are being passed to the stack. Okay, guys? Let's see an example so that you can see this whole thing that I am explaining you in 32 bits. Okay, so when you do a function calling convention, when you use these functions in Windows, the standard call is the way this function works in 32 bits. It's called standard call or CDECL. This basically means that the parameters are pushed to the stack in reverse order, the way I just explained you. And let's see how that works, guys. I just explained you in the previous slides how that works, but let's see that like if this were a debugger. Maybe now you can understand a little bit more, okay? So at the top, you have the main function. You have a function which is called print values. That's the first instruction that's going to be executed. It has 2 parameters or arguments, 1 and 2. Then once it calls it, it goes to the print value here, receives these 2 parameters, print the result, which is a plus b, and then returns back to the main function. Okay, so let's see how that works with the explanation of the stack. So the main comes to the print value. It says, hey, I'm going to call a function. Oh, that means I'm going to create a stack right now, to process this function. Great. So you're going to push in reverse order. Remember, guys, it's in reverse order. So you push number 2. Great. Then you push number 1. Here is EBP. Here is ESP. Great. Now it pushed the return address. That means I already pushed the number 2. I already pushed the number 1. Now I am pushing where I need to return after this function, which is basically at this location, okay, which is after finishing this function. Where should I return after returning from this guy to this position? That's exactly this return address, okay. Now we go into the print value, okay. The stack is exactly as you can see here. It goes process whatever it needs to process. It says, okay, I'm gonna print a plus b. I print it, is 3. Then it says, okay, I need to return. But where should I return? It goes to the stack and it do a pop. You remember the pop, guys? Okay, so this instruction is gonna say, go to the stack, to the last one that was inserted, and here I'm gonna get the address where this return guy is pointing to, so that I can know where should I return. That means, thank you so much for that value, and then the program knows it needs to return to this guy. So you follow me, guys? You follow this? Let's do it again, okay? So let's do it again, guys, okay? So that you can fully understand it. So we are in the main function. We are about to call this function print values. That means a temporary stack is gonna be created that is gonna receive 2 arguments. Then we start. The CPU pushes the number 2 in reverse order, then the number 1, and the last thing is gonna be pushed is the return address. Meaning, after this guy is done, where should I come back to the program? Then it is to this address. Then it pushes that address. Great. I know where should I return. Then I jump into the function. Inside the function, I do whatever calculation it is. In this case, a plus b, number 3. Then says this, okay. Then I need to come back to whoever calls me. How do I know who calls me? Oh, let me go to the stack and pop this address, which points to this return address is actually, is actually an address in the stack. I'm gonna do a pop. I save it, and then I know where should I return. So I do a pop, get the value, and boom, I return here, guys. That's the cycle of a 32-bit stack process, okay? There is another calling convention, which is fast call, which this stored in registers first. The first two parameters are stored in ECX and EDX, and then after that they are pushed on the stack. So instead of these guys, like you see here, is store everything in the stack. Here in this fast call, the first 2 parameters are stored in ECX and EDX, and after that they push it into the stack. So you always need to understand what is the calling convention of the program you are analyzing. That way you can understand, because if, for example, you think that it is a standard call and you're trying to see this pushing into the stack, and you know what, the parameters are being saved in ECX and EDX, then you don't understand how the parameters are being sent to the function, and then you get lost. That's why it's very important, the calling convention. Now, 64 bits is different, definitely. In 64 bits, the arguments in Windows are passed in the registers RCX, RDX, R8, and R9. In Linux is different, but it's also through the registers. The floating point arguments are passed in XM0, 1, 2, and 3. And when you have 16-bit arguments, which is actually bigger sizes, all of them are passed by reference, meaning you pass an address to the function. Okay, so it depends on those, and you will see many exercises of these guys in the lab. The return value, I explained you the return value, guys. That one is in pushing the stack, as you see, but also it depends on how this is being used. Let's see this. In Windows APIs, which is the operating system, we're gonna be doing a lot of exercises. As I said, you're going to be using the standard calling convention. So the function result is stored in the EAX value, which is EAX in 32 bits, and RAX in 64 bits. That's a rule of thumb, guys. That's very important when you start, working with this analysis. Normally, you don't know this. I remember back in the day when I started, it was something that I didn't know, and once you know it, it's pretty cool because, so for example, if you want to know like virtual alloc, you call virtual alloc, you know that after you call in virtual alloc, that basically is gonna allocate memory for you. You know that after this call, if it is 32 bits, is gonna be in EAX the address allocated or RAX address. Okay. So for example, here in 32 bits, you call this virtual alloc, and after calling it, EIP, let's see, EIP is pointing to this instruction. Okay. And this value of EAX is 4170,000, which is the address allocated. And you see this instruction that you remember, guys? It says test EAX. That means, hey, if EAX is 0, jump 0. You remember this, guys? We're combining here all the different instructions. And actually, let's do something before that, guys. Let's do a quick overview here of what I just explained you in this whole class. So when you call virtual alloc in 32 bits, see this, guys. First, there is a push of number 4. Okay. Then there is a push of 1000. Then of this address. And then a push of 0. Okay. And then that means those are the parameters that are being called by the function. And you remember, guys, this was actually sent in the reverse order. That means that this guy 4 actually means, let me see, 4, push. Yeah, you see, here are the real parameters that we are seeing. So when you call push 0, this means 0 here. Push 3FF is this guy. Allocation type is this guy. And push 4 is this guy. That's the way the debugger allows you to explain it. After that, it comes the call. Okay, this call is gonna return to this guy here, and here is gonna be EAX holding the address. Okay, and now this instruction that we saw before is check if EAX is null, because if it is null, that means there was no allocation, and then comes the comparison, right? Jump 0 or jump equal. Remember this instruction? So if the 0 flag is 0, that means this guy was equal. That means was 0, and then I exit. But if this is not 0, that means I have a value, and then I keep executing the program. Okay, guys, we kind of summarize everything into this window of what we have learned in this class. A summary. So we learn about quickly x86 architecture, the functions, the calling conventions, assembly code, basic assembly operands, basic stack operation, mainly for 32 bits, but it's very important for you guys to understand stack. Very, very important. Windows APIs standard call, which is the one being used by Windows. Very, very important. And then, as I said, guys, we're gonna do a lot of exercises for you to keep practicing. Okay. Thank you so much.